Well, welcome everyone to today's Research Takeoff, hosted by the National Rail Research Alliance, or the NRRA. We're really glad you joined us. Today we're using WebEx, and I'd like to remind you where to find some of the controls and how to use it for having the best conversation today. You should see a few buttons at the bottom right-hand corner of your screen where you can see the panelists, see the chat, and then also see the Q&A section. And I'd like to remind you to use the Q&A section if you have any questions during the presentation today. We actually have an additional moderator on who's going to just keep track of those questions and be able to answer those in real time during the presentation if they're able to. And if not, then we'll use our dedicated time at the end for Q&A to go over those questions. So please use the Q&A box and not the chat box, as your chat might come directly to me as the host, and I will not be able to answer your questions about the topics pertaining to today. So please use that Q&A box, and we'll be able to respond to you as quickly as possible. Today we have on Dr. Ken Mazur and Dave Hein, who are going to be talking all about ground penetrating radar today, and go over a couple different applications and scenarios and just some different information about it. And so Dr. Ken Mazur is a professional engineer with over 40 years of experience in the application of non-destructive testing technologies for evaluating pavements, bridge decks, tunnels, and other transportation infrastructure. He's worked extensively with highway agencies throughout the U.S. and overseas, and carried out numerous projects with MnDOT involving both research and pavement and bridge deck evaluations. Dr. Mazur was recently selected as the winner of the 2019 ASCE Wilbur S. Smith Award for his leadership and innovation in developing and providing highway agencies with non-destructive methods for subsurface condition evaluation of highway structures. And David Hein is a consulting civil engineer with over 36 years experience in the design, evaluation, and management of transportation infrastructure. He recently retired from Applied Research Associates Incorporated of Toronto, Canada, where he managed a 90-person transportation infrastructure division in the US and Canada. He's the past president of the American Society of Civil Engineers Transportation and Development Institute and chair of 5 engineering standards committees. He's a longtime member of the Transportation Association of Canada, past chair of the Pavements Committee, and past member of the Transportation Research Board, Pavement Management, Pavement Maintenance, and Pavement Preservation Committees. He's represented Canada on the World Road Association Pavement and Asset Management Committee since 2002. He's also recently stepped down after 10 years as executive director of the Falling Weight Deflectometer User Group. He's been involved in numerous national and international research, evaluation, and asset management projects for federal, state, provincial, and municipal agencies, and many of the public, private, and partnership highway construction projects across Canada and the United States. So thank you to our speakers for being here, and thank you all for being here, and I will turn it over to Dr. Ken Mazur to get started.
Thank you, Lauren. Thank you, Lauren, and good morning, everyone. What I'd like to do, we both like to do today, is talk about incorporating subsurface information into the decision-making process. Traditionally, there's been a lot of emphasis on surface distress. For example, in pavement management, decisions are made almost exclusively on surface distress. But I think we all know that what we see on the surface is the result of conditions below the surface. And the idea here is that the better we understand those conditions and can characterize the nature and extent of those conditions, we can make better decisions. So what we plan to discuss today is a couple of subsurface scanning methods, and then go through some sample applications. So we refer to these methods as scanning methods because they're generally applied at normal driving speed. Ground penetrating radar is implemented at driving speed and detects the layering of the pavement. For example, traffic speed deflectometer can measure deflections, and then integrating this with surface information gives us a bigger picture. And the applications we're going to discuss are to pavement management and to rehabilitation design, and then Dave will talk about the application to in-place recycling and the impact of overweight vehicles, and then I'll finish up with some failure investigation applications. So first I'll talk a little bit about ground penetrating radar. I know the Minnesota Materials and Research Group has done a lot of work with GPR, but for those of you who are less familiar, I'm going to go over it a little bit. So we have the sensing elements in GPR are the antennas. And they transmit radio waves down into the pavement, which reflect off of the different elements in the subsurface and come back up and get measured. The setup that I'm showing here is the kind of typical highway survey setup. The antennas are in the back on this vehicle. Some vehicles they're in the front. But because they can operate elevated above the pavement surface, allows the data collection to take place at normal driving speed. The rate of data collection can be controlled using a DMI, a distance measuring instrument, and you can choose to collect 1 scan per foot, or 4 scans per foot, or 1 scan every 4 feet, whatever you choose. So the rate of data collection is quite flexible. The location of the data is logged with a GPS, which is generally mounted to the vehicle, so that every piece of GPR data has a lat and long associated with it. So when we plot out the data, we know exactly where it is. Below on the left is a typical GPR image. It's kind of a longitudinal slice through the pavement, and it kind of looks like a layer cake where we see whitish bands at the boundary between each of the pavement layers. So what we're seeing horizontally is distance, and vertically is time or depth. And what the analyst does with this data is they track the individual layers, and then the computer software uses those tracked layers to calculate the thickness of the individual layers, which is reported out kind of automatically. So one of the most frequent application of GPR is to measuring the thickness of pavement layers. And I know a number of the MnDOT districts have been doing this sort of work over the past few years. Because we can see a very clear picture of the layer structure, we can also distinguish very quickly differences in pavement structure. So when you go, for example, from a full depth asphalt pavement to a composite pavement, that shows up very clearly. And so some investigations involve identifying the limits of composite pavement, because on the surface it's all asphalt, so you really can't see. Other investigations can take place with GPR. The presence of stripping produces anomalies within the layer structure that can be quantified, so you can use GPR to identify stripping. Voids and moisture in the base or subgrade show up as anomalies and can be identified. GPR has been used to look at deterioration in the concrete under an asphalt overlay, either on bridge decks or pavements, and it's very frequently used to measure the depth and location of reinforcement. Here are a couple of GPR images that show a little more detail. On the left, we have a composite pavement, which has been overlaid. So basically the surface is all asphalt, but the interest was in finding areas that had been repaired, which you can't see from the surface. But with the GPR, you can see these little hyperbolic blips are the rebar for the concrete, and you can see they're absent in this middle section, which is where there's a full depth asphalt repair. So in this particular project, those repair locations could be readily identified, even though they couldn't be seen from the surface. On the right, we're looking a bit deeper, down to about 2 meters, where we're identifying 3 culverts. You can see them by the shape of this reflection, along with the frost taper that's associated with their excavation. Now, I refer to that so far as traditional GPR. There's a newer type of GPR system called 3D radar. The GPR that I showed you had 1 or 2 antennas, and you got a single line of data at a particular offset. With this 3D radar system, this unit, the back of the vehicle here, has actually 21 antennas, each of them 3 inches apart. So in addition to getting quite a bit of detail going longitudinally down the road, which is normal for GPR, you also get a lot of detail going transversely. So certain issues where we need to get information in detail in both directions are very well addressed with this newer 3D radar system. So the example I've shown here is a bridge deck, and what we're looking at is a plan view looking down on the deck at a particular depth, in this case the depth of the rebar. So you can see, for example, in this what's called a depth slice, you can see the entire deck, you can see the joints, and you see evidence of reinforcing, and you can see that rebar pattern blown up for one of the spans here. So you see all the transverse, and you also see the longitudinal bars as well. So quite a bit of detail in both directions is available with this kind of system. The second technology I'd like to discuss deals with measuring deflection, traditionally done using a falling weight deflectometer. More recently now, we've seen the introduction of the traffic speed deflectometer. This is a piece of equipment that can measure the pavement deflection while moving at normal driving speeds. So this allows for making deflection measurements on up to about 200 miles or so of pavement a day. The system works with a series of Doppler lasers, which are mounted forward of the rear loading axle, and each of these lasers measures the velocity of the pavement. And by combining the vertical velocity of the pavement with the horizontal velocity of the vehicle, you can get actually the slope of the deflection curve. And then once that slope is integrated, you actually get the deflection curve. So with this system, every 100th of a mile, you get a deflection curve reported. Quite a bit of information. So the TSD goes quite well with GPR because both of them are getting sort of continuous information. And by combining those two with the layer structure and the deflection, we can then go through back calculation to get the pavement moduli, get the subgrade modulus, and then go on and calculate structural number and remaining life. And at the bottom right here is a plot of remaining life. And by having that kind of information, we could now segment or divide the pavement into subsegments based on remaining life, which in terms of making decisions is a lot more effective than dividing it up based on simply surface condition. And then we combine subsurface information with near surface and surface information. This is a system that does both high resolution video and infrared thermography. The cameras, infrared and video, are mounted to a vehicle that's imaging the surface of the roadway directly in front of the vehicle. The infrared image that I show here to the middle here is showing anomalies associated with delamination in the concrete. The sun hits the pavement, the areas over the delaminations get hotter because the heat can't travel through, and they get picked up very readily with an infrared camera. So that's another bit of subsurface information we can add. And then finally, we incorporate it all into the surface image by stitching together a complete video of the surface. So now we see all the surface features that we're accustomed to looking at, including cracking and map cracking, fatigue cracking, longitudinal transverse cracking, spalling, etc. So now we have sort of the complete picture. We've seen elements of the subsurface and we've seen elements of the surface. So that's where we're starting, and the idea here is to take what we see on the surface and understand that it's caused by something that's going on under the surface. So whether it's weak subgrade or stripping in the asphalt or inadequate pavement structure, voids on the joint, etc. The better we understand what those conditions are and the depth, the nature, and extent, the better decisions we can make about how to address them. So there are various applications of this methodology that we'd like to discuss, and we're going to do that over the next, the remainder of this presentation. So before I go ahead, I'm going to look at some of the couple of the questions. One question has to do with validation with cores for pavement thickness. That's often done. It's not necessary to do the analysis, but the precision can be tightened up by having cores available, and also cores are useful to identify the material types within the pavement structure, which are not necessarily obvious with the GPR. And then a second question is, can the 3D radar look at dowel bars or tie bars? And if so, what accuracy? And the answer is yes, and it's been done. I have not included that in this presentation, but if you send an email or contact us, we can send you some information on that. Let's see. Oh, I see. How is remaining life calculated? It's using AASHTO 93 as the question kind of answered on its own. And can we identify raveling with any of these technologies? If it's not visible and it's underneath a layer of an overlay, it's kind of falls into the category of like stripping, and yes, and I'll get into that a little later. I think that's all the questions that I can detect. So I'm going to move on and talk a little bit about some applications. The first application is to network level pavement management. And the idea here is to make decisions based on remaining life, which seems to me a more sound way of making decisions rather than simply on what the pavement looks like on the surface. And so those decisions, the remaining life would be calculated using information on the pavement structure. So this analysis would be achieved by combining the deflections from the TSD with the layer thicknesses from the GPR to get the various moduli, structural number, remaining life, and then calculate with traditional methods required overlay thickness and remaining life. So we get quite a bit of information here. TSD and GPR provide information every hundredth of a mile. So we get hundreds of data points and a typical thousands of data points for a particular network. So we found it useful to present this information in kind of geospatial sort of way so that it could be easily visualized for both network and project level decision making. And also so they can be aggregated into homogeneous units for management decision making. So this is one example of that sort of visualization. This is showing asphalt thickness on a 1,000-mile network. This is out in Idaho. And this display is using Idaho's GIS system called iPlan. So anybody can go to iPlan and go and look at this data. This is actually showing asphalt thickness and the color scheme is less than 2.5 inches is red, greater than 8 inches is green, and various colors in between. So you could get very quickly a look at what the layer thickness of the asphalt thickness is on this network. But even further, we can take the TSD deflection data that we collected on this very same network, do the analysis, and then calculate remaining life. And this picture shows the remaining life also color-coded, with red being less than 3 years and green being greater than 17 years. So very quickly we get the picture of what's going on. We can zoom in and get quite a bit of detail and actually see things that would be of interest on the project level. And then all of this information, all of the underlying information is there in the attribute tables that underlie these maps, these plots, and you can download that information and get all the details. A second application I'd like to discuss is to rehabilitation design. And in this particular case, the example I want to use is concrete repairs for a composite pavement. This was a 30-mile overlaid concrete pavement section, and it was exhibiting pumping and faulting at the joints and also surface cracking. The client agency needed to select the appropriate rehabilitation strategy, but the alternatives that were available to them differed in cost by several $1 million. So they wanted to make sure they were picking the right strategy and making the right decision and doing the right thing. So we carried out a fairly comprehensive analysis, looking at the thickness of the overlay, as well as the concrete thickness, base thickness, and subbase thickness. Located, there was some full depth asphalt as well as composite. So the locations where the transitions between these pavement types would determine deterioration of the concrete underneath the friction course was evaluated, and location of areas where joints showed evidence of moisture infiltration and voiding were also identified. Surface distress was also mapped and combined with the subsurface information. So this was a fairly comprehensive evaluation, and this slide here shows examples of the type of information that was provided. In the upper left, percentage of area of concrete deteriorated underneath the asphalt versus project station. So you can see it ranged in a lot of areas from 5 to 15% of the year. Some places there was none, some it was quite high, but it gives a fairly big picture of the overall condition of the concrete. On the right here, if you go over to the far right, this is a GPR image of the concrete, and this band over here that I'm showing is the bottom of the concrete, and every joint you'll see a little blip, but at joints that have voids and moisture infiltration, that blip becomes a lot more prominent, and that can be calculated and identified. So this table here shows areas at stationing and coordinates where voids were located underneath the concrete. So that provided the agency with the ability to go out locally, look at these areas, and do any further investigation. And finally, at the bottom here is a map showing both the surface distress as well as the deterioration in the concrete underneath the surface. So with this kind of information, the agency was able to go out and do some targeted local confirmations using FWDs and coring, and they were able to come up with a rehabilitation design that they felt was appropriate for the conditions that they were observing. So at this point, I'm going to turn the microphone over to Dave. Dave's going to talk about in-place recycling.
Thanks very much, Ken and Lauren, for the introductions, and all of you folks for spending a little bit of time with us here today, talking about pavement rehabilitation and rehab, et cetera. One of the other really useful applications of GPR technology is in helping supporting things like in-place recycling efforts. A lot of what we do these days is not so much designing new infrastructure, but rehabilitating that we've been constructing over the last 40 or 50 years or so. And thickness is really important in technologies such as cold in-place recycling, be it and partial depth recycling, be it with the emulsion or with the expanded / foamed asphalt. And for the reasons there are is that the asphalt thickness itself, we typically want to recycle as much as we can in situ. Helps with reducing waste and less expensive than many other techniques. And one of the key aspects we need to have is the thickness of the asphalt in particular. And so we typically will go out there and to design our recycling efforts to take not all of the asphalt layer. We need to leave some materials behind for a couple of reasons. One being we need something relatively good to support the recycling equipment, because some of this, you see the train in the picture here is very long and quite large. But also because we design our recycling efforts to add emulsion or expanded asphalt to optimize the remixing of the material and laying it back down on the roadway. So a lot of these projects, longitudinally on the roadway, most people don't really know exactly what the thickness materials are. Maybe they did 50 years ago when they first laid them down, but ultimately we typically do some cores, or maybe boreholes, but at least cores to validate the thickness of the materials. But those are one single point, and we can't, we may be doing 20 miles of recycling on a particular project. And so knowing what the thicknesses are, so we can either reduce the depth of recycling or optimize the depth first of all, and then either reduce the depth in areas that the asphalt may be thinner, or potentially go out and pre-mill the areas to get a more uniform pavement structure. Uniformity is extremely important in pavement structure rehabilitation because we want it all to basically act the same. If it all settles a little bit, that's fine if it's on a rural highway, but ultimately this is where we use this technology to provide a constant thickness. Go to the next slide, Ken. So we go down the roadway, collect data. This data can be done, as Ken showed you, with the 3D radar, where you're doing an entire lane width potentially. It is more expensive to collect data using that type of equipment than a traditional GPR device. So you can also go down the roadway multiple times, and I see that was one of the questions that was asked earlier. Do you go down it with one radar device in one line? Well, we can offset that on the vehicle, or the vehicle itself being offset potentially, and we can take multiple passes longitudinally down the roadway. If you do 2, 3, 4, 5, maybe maximum, you can then do heat maps basically of the GPR data. So in this particular case, you can see longitudinally down the roadway that we have differences, two differences. One, we have a difference in the thickness of the asphalt looking at milepost 30 to 33. In terms of clearly in the graphic above, you can see the differences in thickness. Beyond 33 to the 38 range or so, it's a little bit thicker. And then also it's different lane across the lanes. There may have been some widening happening. Other reasons may have made different thickness. Maybe it was originally a crowned roadway that was turned into a sloping all in one direction type of roadway. And so clearly we can see there are differences in terms of the heat map here that will give us information about the thickness, so we can optimize our recycling. Next slide, Ken. Utilization of GPR data in conjunction typically with deflection data, be it the TSD that Ken mentioned earlier, or potentially conventional falling weight deflectometer type deflection data. And everybody's got this problem: overweight and super heavy loads. Ultimately, we put load restrictions on our roadways to protect the roadways so that we will not consume all of its life. In the northern environment, certainly in Minnesota, we have spring load restrictions, and a lot of work has been done actually in Minnesota on spring load restrictions, contrary to the desires of the trucking industry, obviously, because when roads are frozen, a lot of high stiffness, it's not a problem. We can move loads with minimum damage to the pavement structure. But in the summertime, when we've got the water out of the pavement, it's well drained, it's going to have pretty decent structural capacity. But in the springtime, that very short period, maybe 4 weeks, 6 weeks, maybe some places 2 months, we can consume 50, 60, 70% of the life of the pavement in that very short period of time, because we've got water in the pavement. It was frozen, it's starting to melt. That water acts like a lubricant between the individual aggregate particles and the soil particles. And so they're in its weakest condition. So we don't want to have heavy loads, so we slap on spring load restrictions. The trucking industry is not happy with us. We want to make sure we get them on before it starts to unfreeze. We want to take them off as soon as we can. So a lot of people do a lot of work over the years in evaluating that infrastructure to get the right time when we can allow the trucks to go back on. So we have two categories basically: overweight, simple overweight. The picture in the top graphic there, I call it a garbage scow. It's basically compressed trash being moved to a disposal facility. They can be other things like wind farm activities, all the concrete trucks using rural roads. It can be shale fracking, which of course is a big thing in North Dakota, Pennsylvania, southern Saskatchewan, et cetera. And then we have super heavy loads, which are beyond all of this. So the regular overweights, we have overweight permit guidelines. We allow the truckers to do this. We may charge them a fee, typically not so much. They argue that they pay taxes, so they shouldn't have to pay more than anybody else. And they occur for a short period of time, or one-offs, like when you're building a wind farm. The super heavy loads are those that are substantially above the legal axle load limit. And so there are specialized pieces of equipment and stuff that move them. In order to analyze and evaluate the potential damage that occurs, you need to have information about the pavement structure. Did some work in Pennsylvania a few years ago, and when they were looking at shale fracking, we were calculating pavement damage or consumption in the billions of dollars per year. So this is big money. So ultimately, we need to know something about the pavement structure. Go ahead, Ken. So I've got basically three different methods that we use to calculate potential impact. And the most common one, and a couple of questions earlier were asked about the methodology for structural capacity or remaining life. And AASHTO 93 is one of the easiest ones that most people use. I call it a simplified method. It is very coarse. It's based on research and work that was done back in the 1950s, 1960s. It is being replaced nowadays by mechanistic design, pavement mechanistic design. And what we want to do is collect data. Particularly, we need pavement structure information, because that's converted to layer coefficients and the structural, the modulus elasticity of the individual layers that turn into layer coefficients, and then they may be discounted based on the condition of the pavement. In other words, the asphalt may have a layer coefficient of 0.4, 0.42, and you're going to assign it something like 0.3. So the condition is part of the information. It may be based on structural capacity. So using AASHTO 93, you can use the in situ structural number, the SNEF, the effective structural capacity, and assess some sort of damage to it. So we look at, here's what the in situ is, here's what the vehicles that are going to be using it, what is the remaining life, what is the consumption of that remaining life of the pavement. And it's very different if it's a major interstate, that are built to handle loads without spring load restrictions than it is with a rural roadway or rural highway. Rural highways, one pass of this vehicle may consume 20, 30% of the life of the pavement. And so, this happened, and I know from personal experience in Pennsylvania, when all of a sudden we've got all the water trucks and these concrete trucks and the sand vehicles for fracking, et cetera, literally destroying the pavement, with the number of loads they have in the period, and they were literally pushing equipment out with dozers because they got stuck in the pavement. So especially with the lower volume roadways and the thinner pavement structures, you could cause significant amount of damage. So based on EASL, relatively simple. Next one. So then we have what I call the mechanism. Well, it's a pavement ME design, mechanistic design, and this has been used around the planet since the 1970s. The guy that taught me how to do this was Per Ulitz from Dynatest in Denmark, and he was doing it on a programmable TI calculator back in the 1970s. So this is not new. It is newer to North America than many other countries around the world, think France, South Africa, Australia, et cetera. And so a big effort was made starting back in the early 2000s to move to, because we have computing power, to move to more realistic design. It's not the deflection that causes the pavement to crack, it's the bending that occurs, the strains that occur in the pavement that cause it to crack. And so when we're looking at moving some of these other heavy loads, we can use the new mechanistic design. It's got a module in it that allows you to do non-standard vehicles. Or you could do this using other techniques, of course, not just pavement ME. And so we take into account much difference in traffic. Traffic, we no longer use easels, we use axle load spectra, which is the individual axles themselves and the quantities of them and the weight on individual axles, because each of those different axles cause different stresses and strain. So we can use the ME design to calculate things like what additional thickness would I have to apply to the pavement to get the same type of stresses and strains that we would have had we not had those vehicles. And so by doing that, we can assess, additional strengthening that's needed, maybe 10, I don't know, a quarter of an inch or 20 or an inch of material, and we can assess that cost and then assess that cost and lay it on the people who are using the roadway and consuming it, that normally would not have been doing that. Next slide, Ken. Then we have the more complex, the super heavy loads. Now, again, here's another reason why it's really important to have the pavement structure, because the methodology that I'll show you here that we use to calculate stresses and strains is specific to the individual load. So we've got one huge cracker that's used to convert oil into polyethylene or whatever, polypropylene. And so they're not going to be doing this on a continuous basis. They're going to be doing it once. They're going to move a piece of equipment that was built in point A and move it to point B, where it's going to be provided in an industrial facility. And so some of these facilities are very rural, and they go over large areas of roads. So you may looking at a movement of a vehicle that's going to go a couple hundred miles. As much as possible, we put them on barges or boats, sometimes rail, but usually there's elevation issues with that, and so they're moving down the roadway. We can move power lines higher, or other elements. We can plate the pavement to make sure we don't crush the culverts and stuff like that. So pavement structure information is really important, because methodology to calculate the stresses and strains takes a long time. So we have to develop what we call representative pavement sections. And so we don't go out and I had a client once that asked me to analyze 1,000 miles of road using pavement ME every 500 feet. Well, this would take the rest of my life probably to do this, or massive amount of computing power to make that happen. And so developing a representative pavement section is really important. Next slide, Ken. We characterize the pavement structure. We look at the cross section you see on the top here. I mean, this is a element that is going to be moved during frozen conditions. How much frozen pavement do we have? What's the surface that's not frozen? In the individual vehicles, you see the axle loads on the bottom left-hand side there. We've got a substantial number of axles. The equipment is different. It's used to level the weight over all the axles more evenly. The rubber in the tires is 10 times the thickness of the normal rubber for a tire. Very, very thick walls in inches in terms of thickness that don't allow the vehicles the tires to spread out. And so their impact on the pavement structure is really, really important. And I can't do this every 500 feet. It's absolutely physically impossible because of the computing power. Next one, Ken. So we look at them, and we will do a more detailed stress strain analysis using much more sophisticated computing power than the pavement ME design. And we're looking at individual impacts of the vehicle. The graphic on the bottom right is basically a multiple axle. So you're looking sideways at the deflection of the pavement as this giant vehicle comes moving along, and there may be 20, 30, 40 axles in a row. And so each axle interacts with each other in terms of the overall impact on the pavement structure as a whole. And then also you have issues with the stresses and strains at the surface, because a lot of times what happens is it bends upwards between the tires. So not only do we get strains on the bottom of the asphalt, we get strains on the top of the asphalt, and this has really become something that we've paid a lot more attention to in the last 10 or 15 years, because we can have top-down cracking, which we traditionally, in the 70s and 80s, never thought about top-down cracking. It started at the bottom and went up. So that graphic is showing you the curvature, the deflection that's happening at the beginning as that big vehicle's moving across it, and then individually in between each tire. And the reason it goes up and down like that, like the dragon tooth kind of thing, is that we're getting in between the tires. You get some relaxation, then you get next tire loading, some relaxation, next tire loading, etc. And you can see the maximum strain in this particular case in the graphic above is at the top of the pavement, not below. So we do this, and we can do this at maybe a few locations. One vehicle that we moved recently was just under 4 million pounds, and it was moved over more than 200 miles of highway in a provincial thing up in Alberta. where they were building a polypropylene cracker, basically. And the analysis of this, the computing analysis, doing it dynamically, actually at the impact of a moving load, it's different if it moves slow or fast as well. And so this took literally a couple of months of computing to do one analysis. So you need to have pavement structure information to select not only the worst, not the best, but usually something like the 80th percentile of the pavement thicknesses. And so how much damage we're going to cause. And then what happens if the whole pavement goes down in the rural setting by, settles by an inch because of this vehicle? As long as it's not bending, it's okay. It's fine. The whole thing can compact more. Maybe it's even better for the pavement structure, but ultimately, we want to assess some sort of damage fee. And so the analysis here was actually paid by the mover that wanted to move this thing because it was dictated that you cannot move these vehicles unless they have this analysis completed. And then the next more difficult part is, well, how much damage are they causing? And so translating that stresses and strains to damage and actual costs. One of these I did back in the 1980s was a steam generator for a nuclear power plant that was built in Canada and shipped to Florida. And it went over 8 different municipal agencies' roads, and my calculation back then was the consumption of one of these loads was about $2 million in 1986 dollars, so a lot more now, and the permit to move it was $50. So user pay is kind of where we want to go with this. Go ahead, Ken. I'll hand it back to you to talk a little bit about the failure investigations.
Discussing application to failure investigations. I got 3 different examples here. This was an interstate that was experiencing premature failure. There was a belief that it was a drainage problem, but the exact nature and extent of it wasn't exactly clear. So we addressed this by doing 2 types of GPR surveys, one going transverse to the roadway at various stations along the project, and one going longitudinally down the roadway from one end to the other. And what was learned here from the transverse surveys were that in the area where there was damage, the drainage pipe, instead of being located in the shoulder, under the shoulder where it was supposed to be, was misaligned, and it was underneath the wheel path. So it was getting beaten on by the truck traffic. It eventually got damaged, got clogged, and then moisture buildup and damage occurred in other places. Then the next question was, okay, that's the why, and how far, how much, how extensive, is the damage. And so we used the longitudinal GPR to calculate what's called the dielectric constant of the base material. And then with the availability of some lab data on moisture content, we could calibrate the GPR to base moisture content, and we could very clearly see the areas where the moisture content was above normal. So that gave the agency the ability to focus the rehab in the area where it was actually needed. Another application was in a flooding area. City alongside Leclerc, alongside the Mississippi, experienced flooding. It had concrete pavements, and after the flood, it was very clear from the surface that there was some damage. Some of the slabs were settling, and so but the question is, well, that's what we see, but what about what we don't see? And what do we have to do to kind of address what's going to happen as well as what's already happened? So this project was addressed also with GPR, looking at the thickness of the pavement and also detecting voids using both a combination of GPR plus 2 ultrasonic techniques, impulse response and impact echo. And then the areas of questionable areas were identified. Subsequent coring was carried out to validate these results, and this is one of the outputs of that. So on the upper plot here, the areas, what's shown are the areas in one of the roads where there was a high likelihood of voiding. So it could really kind of zero in on those areas. And then in the plot below is basically a contour plot of concrete thickness. So here's the thickness scale. So this information gave their consultant the information they needed to design the rehab. Finally, I want to talk a little bit about stripping and asphalt. That's a type of failure that's of concern, and it's caused by moisture infiltration into the asphalt. The water gets in between the asphalt layers. The vehicle pressure plus the moisture strips the aggregate from the asphalt, particularly if the aggregate is sensitive to that phenomenon, and then you wind up with sort of a layer of rubble, which you might see here. And then here's a core with multiple layers of asphalt, and here's an area where there's stripping. So the issue is, generally it's known that there's stripping, but the question is how extensive is it and what's the depth? So this can be addressed by using either the 3D radar system I discussed before, or the conventional radar system by collecting multiple lines of data at different offsets across the lane, and then analyzing the data to show the locations and extent. So the methodology was developed initially in a SHARP project with testing at the National Center for Asphalt Technology, where they actually took some RAP and simulated stripping by a very open graded RAP layer, and then they overlaid this RAP with the next layer of asphalt. So in plan, these were the quote areas of stripping. This was the GPR slice image, and you can see those areas of stripping are showing up, plus other areas where there was moisture infiltration. And this is sort of a numerical analysis result showing a map of where some of these locations are. So this was the foundation of that methodology, and then it was applied in Minnesota on Trunk Highway 7, which had experienced stripping in a number of locations. And using that methodology, we were able to map the upper layer of the top 4 inches and the bottom 4 inches. It was about 8 to 9 inches of pavement, and show areas where there was high probability of stripping. And these are where cores were taken, and the cores correlated with these maps very well. So that's another application to failure analysis. So basically, just to wrap up, the message that we're making here is that by looking at the subsurface and combining it with what we see on the surface, we can make better decisions and reduce costs. We can, at the network level, we can reduce life cycle costs by making better decisions. At the rehabilitation level, we can optimize the rehab design by basically fixing the right problem and not overdoing it or underdoing it. We can, as Dave talked about, characterize as-built data to avoid changes during construction by characterizing how much recycling is necessary to address what's already there, and also to recover the cost of oversized loads by quantifying the damage. And finally, we can address pavement failures by accurately assessing what the causes are and addressing those causes in the most effective way. So that finishes up our presentation. I'm going to take a look.
There are a few here, Ken. I can just kind of paraphrase them for you, maybe.
Okay.
There was a follow-up question regarding the use of cores, and so if we don't need to use cores, can we read the plots directly, or how accurate are the results if you don't do coring?
You can read the plots directly, but that's sort of an approximation. But when you track the layers, as I showed, it calculates actually the velocity of the radar in the pavement and gives you a much better quantitative result. Typically, without any cores, the difference between the GPR thickness and the actual thickness has been found to be less than 10%. With cores, you can do a little calibration and tighten that down to 5 to 7%. So that's kind of like the range. That's what the cores buy you a little more precision.
Follow-up question from Deepak here asking, can GPR determine soil types? If the soil is clay, i.e. expansive soils, can it give any information pertaining to the influence on distress or on the pavement?
GPR measures what's called the dielectric constant of the material. And if there's a material present that has a very distinctly different, like going from a granular to a clay, if there's a very distinct change in dielectric, that might be useful in suggesting that there's a different material, but it can't really tell you what it is. It doesn't have that sort of diagnostic information.
So if you have something like a fat clay, which would have a natural moisture content of 30 or 35%, and you see that the values are very uniform, it means you can't tell that it's clay necessarily, but you can tell that it's going to be uniform, or areas that might be dry, or so that the variability may be able to be assessed. Infrared, there's a question about a concrete pavement using the infrared technique to find structural anomalies for repair. Do you use GPR and infrared in conjunction with each other?
We do for bridge decks, and they kind of complement each other because the GPR detects corrosion and chloride infiltration, whereas, so they detect kind of the problem that's causing the delaminations, whereas the infrared detects the delaminations themselves. So the combination kind of shows you what's going to happen as well as what's already happened.
Question from Barry asking about the size of the voids in concrete. So what is the, how big do they need to be before you can actually see them? Yeah.
So yeah, the primary detection is the moisture that has gotten in to cause the voids. With that, you don't really need that much of a void because that wet base is showing up regardless of the depth of the void. If there's no moisture involved, then the void has to be larger to be seen, maybe half an inch to an inch. But with moisture, it could be an eighth of an inch, or not even there yet. Just water's getting in.
There's some work that we're doing currently that is, so we have a concrete pavement that had cores taken for quality assurance and thickness, and the people that backfilled the cores cheated, I guess you'd say, and they put aggregate in the bottom of the core hole and then filled the top piece with concrete. So we're using the 3D radar across the entire lane to identify the core locations, first of all, then also, is the core full depth concrete or is it partly aggregate and concrete? So another application of that. Adam's in answering some of these questions as well if people are monitoring it, but I'll ask him because we still have a little bit of time left. And so the antenna across the roadway, we talked about that one. The accuracy of GPR, you mentioned already the answer to that, I believe.
I don't think I answered the antenna Thomas's question. One antenna versus several. So yeah, if we're just measuring thickness, we generally just go down the center line or the right wheel path or whatever. But if we're looking for something that's spread out along the width of the pavement, like stripping, or there's some interest in seeing the variation in thickness across the lane, so we have a 2 antenna vehicle, and if we do 2 passes on a lane, we basically get 4 lines of data spaced at about 3 feet apart. So that's the typical coverage for a more detailed survey.
Stacy asked about the general question, the accuracy of GPR. You kind of covered that up earlier.
Okay, yeah, I in terms of thickness, I think I mentioned the accuracy with and without cores.
The one with Thomas here, I'm not quite sure I understand the question, but it says the situation I had in mind was remediation overlay of asphalt over concrete where widening had been done, RT in some instances, or right and left in the other instances, I guess, looking at, can you detect where that widening was done?
So, yeah, that's, if you have a road that's been widened and you want to know, you can't tell anymore where the boundary between the old and the new road is, you can do several lines down each lane and see where the structure starts to change. So you would, you're doing a right lane, 4 lines, middle lane, left lane, and you see between the, the left wheel path of the right lane and the right wheel path of the middle lane, it's a totally different structure. You know that somewhere in between them, that's where the widening occurred. But and then if you can and close the road for a bit, you can do a scan transversely across the road and find exactly where that change in structure is.
Use this application in my neck of the woods because a lot of lane widening was done when they changed the width of the lanes here, and they did asphalt widening in a composite pavement, so you'd have an asphalt plug that would be beside it, and you can definitely tell the difference of that as you cross the road.
Yeah.
Another question from Peter here is about can the infrared detect unseen delamination cracking in concrete?
Oh yes, I mean that's really the idea, is that you can't see the delaminations because they're generally going on under the surface, and you see them when they spall, but you want to catch it before that, and they show up very well with the infrared. So that's the whole idea. Yeah.
Yeah, and Thomas followed up saying that his question was regarding a 2-lane road that was originally concrete 10 feet wide lanes, and the AC was 12. And yeah, that's exactly the situation Ken and I both just described. So
Okay.
yeah, I guess the answer is yes. That's all the questions I see here currently, Ken.
Okay, Lauren, did you want to open it up for anything else, any more?
Yeah, and I actually did get a question privately in the chat, and then I just got another one as well. So this one comes from Kevin McMullen. Can you detect the location and size of clay balls in concrete pavements or voids around steel in concrete pavements?
Clay balls.
Mm-hmm.
Yeah, that's well, it requires a lot, because they're small. It requires a lot of detail. A while ago, we did that, but we did that with a hand push type of GPR, doing lines of data spaced transversely about 3 inches apart. So we get, like 100% coverage to catch them. More recently, we've been working on a project with Dave to use the 3D radar system, which has that level of detail built into it. So it's doable, but it does require fairly intensive coverage to catch that level of detail.
We can certainly collect the data for this type of thing, but the analysis is important, and the attention to detail of the analysts and doing the evaluation and making the call is the important part here. So I mean, anybody can collect data, but it's the analysis that's the important part.
And I see a question about, can infrared be done at highway speed? So traditionally, it was done at rolling speed, 5-10 miles an hour. But recently, the infrared camera technology has improved dramatically. So we can now capture images at driving speed that are as crisp and clear as what we used to have to go slow for. The integration time of the infrared equipment has dropped considerably. So now we can do these surveys at highway speed.
Okay. And I do have one more here in the chat. To what extent do the current antennae make a clear statistical distinction at the concrete granular base interface when their moisture contents are almost always similar?
Okay, I missed the beginning part of that. Could you repeat that?
To what extent do the current antenna make a clear statistical distinction at the concrete or granular base interface when their moisture contents are almost always similar?
Yeah, that's a very good question. And actually, compositionally, concrete and aggregate base are almost the same. The concrete has a little bit of cement in it. So there are a lot of situations where you cannot see the boundary between concrete and aggregate base, or even worse, concrete and cement treated base. Generally, we have to use the ground coupled antennas, which pump more energy into the pavement to get that boundary to show up. But there are situations where you just can't see it.
Okay, well, we are just past the hour here, so I want to be respectful of everyone's time and wrap it up here, but I imagine that both Ken and Dave are happy to take additional questions via email. And if you need to email me, I can certainly pass those on to them. And I will just pop my email in here. So I just sent that out to everyone to be able to see, and I can direct any additional questions to them. This session has been recorded and I will be putting it up on YouTube by the end of the week. If you want to come back and watch anything else or revisit some information. I want to thank Ken and Dave for their time today and for sharing this information, and then as well as Adam for helping answer some questions during the presentation. Thank you all for joining us, and we will see you next month on March 16th for our next Research Pays Off.
Thank you, Laura.